Hey everybody, welcome back. Let's go ahead and do section 1.5A where we're talking about polynomial functions and complex zeros. So let's do a quick little reminder of what zeros and x-intercepts and linear factors are. So remember, if we have P of A where sum A gives me an output of 0, we call this value of A, whatever that was that gave us our value of 0 as the output, is A0. The other way we can call this or a root. So these words are used synonymously in math. So if someone says a 0, it's the x-intercept. But also if it's a root, it's also the intercept. And then that point is called A comma 0, right? Because it's on the x-axis. If A is the real number, then this factor, x minus A, is a linear factor. So that's how they work together. Remember that, for example, if you had, something in factored form where you set it equal to 0, those factors, let's say x minus 2 and x plus 3, you would say x equals positive 2 and negative 3 are your zeros. Okay. So let's talk about these next. So I'm not going to teach you guys how to factor, but if you need to remember, here's a quick little example. So we see that this is a cubic function. So we're going to go ahead and start to factor. In order to factor this, we always look for a GCF first. So with our GCF, I can see we've got x to the third, 2x squared, and 8x left. So I can take out an x in my GCF. That leaves me x squared minus 2x minus 8. What's left here is a quadratic, so I'm going to use x factoring for negative 8 and negative 2, and I see that negative 4 and positive 2 will work this out. So this now becomes x minus 4x plus 2, bring out that greatest common factor. So keep in mind, if I'm looking for the x-intercepts, that's AKA to find the zeros. Remember that the output for these specific inputs means they're 0, so I'm going to set it equal to 0. Right now, in order to solve this, we use what's called the zero product property, where I know that if these values multiply x times x minus 4 times x plus 2 equal to 0, that means each of these have to equal 0 in order for a product to equal to 0. So what I'm going to do is I'm going to say, okay, I know x has to equal 0. I know x minus 4 has to equal 0. And I know x plus 2 has to equal 0. Now that's really manageable to be able to solve x equals 0 as a solution. If I add 4 to both sides here, I know x equals to 4. If I subtract 2 to both sides, it's also x equals to negative 2. And those are our x-intercepts. Now let's look at the next one. Given the polynomial function h of x is x squared minus 2x minus 3, what are all the intervals where h of x is greater than or equal to 0? So keep in mind we're still dealing with 0, but we're not just looking at specific points. We're looking for where it is above 0 as well. So we're still dealing with a quadratic here, so we're still going to factor. What multiplies to negative 3 adds negative 2? It's 3 and, 1, where 3 is negative, so we know we can factor this. And we're still going to set this equal to 0 to find those x-intercepts because we want to know where it crosses the x-axis. Oh, wait, real quick, back up. On this last one, we need to sketch it. So we've got x equals 0 here is on x equals 0. X equals 4 is here, 1, 2, 3, 4. There's our x-intercept. And then this last one, x equals negative 2 is here, okay? We also know, remember, that our end behavior for x to the third means because it's positive and odd, means we go up to the right and the left will be in the opposite direction. So we go to our rightmost point and we're going to go up from there. That means we also go to our leftmost point that we have. We know it's going to go down. And then now we're going to connect them to go from 0 to 0 in order for this to work for the end behavior. Let's look at this next one. So picking this one back up, again, zero product property tells me that here x minus 3 has to equal 0 and x plus 1 has to equal 0. We get x equals 3 and x equals negative 1. I'm going to sketch that on my graph. So x equals 3 is right here. and x equals -1 is here. Remember that this is called a positive even, which my end behavior says we're going up to the right because it's positive, and it's even so it matches. So on my rightmost 0, we're going to go up to the right. And on my leftmost 0, we're going to go up to the right as well, which means the only way that we can connect between those two is if it dips below and we have a minimum underneath those two. Now, if I want to talk about the intervals, we want to make sure we answer the whole question. Intervals on which it's greater than or equal to 0. So remember, greater than or equal to 0 is where is the graph greater than 0? So it's here and here. So where do we see that? So let's talk about interval notation. So this is at -1. So I know for x values from -infinity to -1, and including -1, it's greater than 0. We see that here, right? And then also here at 3 all the way to the right. So we say also from 3 to infinity as well. And that's our interval. Let's talk about multiplicities now. So multiplicity means if a linear factor is repeated a certain amount of times, the corresponding 0 of the polynomial function, I'm going to move this over here real quick, 1 second. Here we go, has a multiplicity of n. So let's look at this. So if p of x is x plus 1 to the second, this has a multiplicity of 2. Okay, also here, this is our multiplicity of 3. The multiplicity of x plus 4 is a 1. Here's what this means. If we have an even multiplicity, the graph will bounce off of the x-axis at x equals a, aka where the 0 is. So if we see an even multiplicity, it will bounce. So let's go ahead and graph these. So I know if I'm solving this, I've got x plus 1 equals 2. If I'm setting it equal to 0, x minus 3 equals to 0, and x plus 4 equals to 0. That gives me x-intercepts of -1, positive 3, and -4. So I'm going to sketch those. -1, positive 3, and -4. Okay. Once I have these zeros sketched, I'm going to be looking at multiplicity. So I see here at -1, it's a multiplicity of 2, which because it's even, it's going to bounce, okay? For here, it's got a multiplicity of 3, which means it's going to go through. It's not going to bounce. Same thing here. We have a multiplicity of 1. It's going to go through. It's not going to bounce. So now this is really important so that we know how to sketch this. We're going to look at the end behavior. So remember from last section, to find our end behavior, we do need to know what our leading term looks like. So if I've got here x squared, so I'm going to write that here, x squared times x to the 3rd, and that's times x to the 1. We get a total of x to the 6, and it's positive. So it's positive and even. So again, to our right side, it's rising. It's even, so it matches. And I know I have a multiplicity bounce at -1. So that means here, I know when my graph goes through, it's going to go through the -4, but as it approaches -1, it's going to hit -1 and then bounce off of it. And then because the multiplicity at 3 is an odd, it also goes through that. So let's go ahead and sketch that. So again, we go through the 4, up to the -1, and it bounces, and then again through the 3, and that's because of our multiplicities. So another way of thinking about this is to look at the output values, okay? So let's look at what we would look at if we were trying to sketch this, okay? So first of all, where is p of x less than equal to 0? So we know it could be equal to 0 or negative. Okay, also we want to know what are the zeros for this function. So I know x minus 2 would give me x equals to 2, x equals to 5, and x equals to -7. Well, we see that this has a multiplicity of 1 at 2. At x equals 5, there's a multiplicity of 4, which means it's going to bounce. And this also, x equals -7, also has a multiplicity there as well. If I just roughly sketch this on the x-axis, where we have x equals 2 is our 0, x equals 5 is also a 0, and x equals -7 is also a 0. Now we want to see, okay, again, what was your end behavior? End behavior is x to the 1 times x to the 4th times x to the 7th, or x to the 1. This gives me a positive x to the 6. So I know positive means we go up to the right, and it matches on the left. And then we know because x equals 5 has a bounce, it's going to not go through it, it's going to bounce off of it. And then everything else it will go through, so it's going to curve around, go through that x equals 2, and it's come back around, it's going to go through that x equals -7. All right, let's look at complex zeros. So complex zeros is this idea that polynomials have a certain degree, and they have exactly and complex roots when we are counting multiplicities. Complex roots refer to both real and non-real zeros. If there are any non-real zeros, they always come in conjugate pairs. We've talked about this before, conjugate pairs. This means that there are either no non-real zeros or an even amount of non-real zeros. This is super important, okay? So let's say, for example, something is a quadratic, therefore it has a degree of 2. This is telling you we have a total of 2 zeros that we need to look for. So in this example, there are 2 zeros here and here. So because we can see them, we call them real. They cross the x-axis, which means because we've already met our total of 2, there are no non-real zeros. If I look here, as I look at this quadratic, I see it crosses the x-axis here 1 time. But remember, it's bouncing off that 1. So we know there's a multiplicity of 2, therefore there's also 2 real zeros, even though we only see it once because of this multiplicity of 2 that bounces, and we have 0, no non-reals. Lastly, if I look at this one, I see that there's nowhere on this quadratic where it's crossing the x-axis, which tells me there are 0 number of real zeros, which means because I have to have a total of 2, there must be 2 non-reals. Let's look at this cubic one. So again, if the degree is 3, we have a total of 3 zeros that we're looking for. So with this first one, we have 1, 2, 3 real zeros. And because we've already met our max of 3, there's no non-reals. Here I see, okay, it went through it, which means we only have 1 non-real zero, which means in order to make up the other up to 3, we're going to have 2 non-real zeros. And then lastly, I see 1, 2, and because it bounces, we know there's a multiplicity of 2, it's another 2 zeros there. So we see 3 real zeros and 0 non-real zeros. And again, the idea is that the sum of these numbers add to 3. So 3 plus 0 is 3, 1 plus 2 is 3, 3 plus 0 is 3, and so on. So let's try this one as an example. Go ahead and push pause and try this one on your own. The degree of the polynomial is 8 with a real 0 at x equals -10, x equals 5, and x equals 16, where x equals 5 has a multiplicity of 2. So remember, this has 1 multiplicity, this has 2 multiplicities, this has 1 multiplicity, okay? How many non-real zeros does a polynomial have? So again, we have a degree of 8 because we have 1, 2, and 1 multiplicities at the real. That's 4 real, and because there's 8 total, there has to be 4 non-real for a total of 8 zeros, both real and non-real. So let's talk about non-real zeros. So if it's non-real, we have this complex number, a plus bi. Then it also means that its conjugate, a minus bi, is also a 0. So for example, if you have this non-real 0, which is -3 plus 6i, so -3 plus 6i, you're going to see what's inside is that plus. So we're going to go -3 minus 6i. Okay, secondly, if this is 4 minus 2i, meaning the minus is that middle term, then we're going to go use 4 and 2i, but the middle will now be plus. And if you're wondering where this comes from when we solve for a quadratic. If you remember, x equals negative b plus or minus square root of b squared minus 4ac all over 2a. Where the i's come from is in here in the root. If there's a negative in there, that would be your I. But see how there one's a plus and one's a minus? That's where these pluses and minuses come from, that it has the same real term b and the same I term in the root, but one's plus and one's minus. All right, let's turn the page. We're almost done. So let's talk about what does it mean to find the degree of a polynomial. Okay, so let's talk about these successive differences. This is very similar to what we did with average rate of change. But in order to find the degree of the polynomial, we need to find the degree if we have successive differences and we find where they start to become constant. Let me show you what that means. So remember, a constant means they do not change. So let's find the first differences of these outputs. So from here to here, what are the differences of these output values? Remember, this only works again if the differences are 1 in the x value. So here we go. From 0 to 1, we add 1. From 1 to 4, we add 3. From 4 to 9, we add 5. From 9 to 16, we add 7. From 16 to 25, it's 9, and so on. Now, none of those are the same, so we're going to need to find the second difference. So from 1 to 3, we added 2. From 3 to 5, we added 2. And we can see that there's a pattern here. Because now, in our second difference, as we see the same number, we know that the degree that we found is equal to the layer of the second difference. This is a degree of 2. If I look at this one, let's find our first difference. So from 50 to 49, it's minus 1. From 49 to 38, it's negative 11. 38 to 5 is negative 33. Negative 67, negative 113, and negative 171, and so on. So we know because we haven't found the same number, we're going to have to find the second difference. So from negative 1 to negative 11 is negative 10. Negative 11 to negative 33 is negative 22. Negative 33 to negative 67 is negative 34. Here's negative 46 and negative 58. Because these numbers are not the same, we have to find a third difference now. So let's find it. This is going to be negative 12. Ooh, this one's also negative 12, and so on. So because that third difference are all the same number, this tells me that the degree is 3 at that layer of difference. All right, guys, that's all for today. See you in class.